Today, we are diving into one of the most fundamental processes in the entire universe, gamma decay. Now, this is a burst of pure energy that literally brings stability to the atomic world. And, you might be surprised, it has some seriously powerful applications in our everyday lives. So let's get right into it.
So, let's start with a simple question. What happens when an atom's core, its nucleus, just gets a little too, well, excited? Think of it like a spring that's been wound way too tight, just buzzing with energy. It can't stay like that forever, right? It has to find some way to release all that tension and just calm down. And how it does that is exactly what we're here to talk about.
You know, our story usually kicks off right after another atomic event has happened, something like an alpha or a beta decay. After all that, the nucleus is changed, sure, but it's often left in this jittery, high-energy state. It's unstable, kind of like a wobbly spinning top. It is desperate to find its balance again.
And this image right here, it perfectly shows the solution. On the left, you've got this parent nucleus all wound up in its excited state. Now, to relax, it doesn't spit out a particle or a chunk of itself. No, instead it just lets go of its extra energy as a pure packet of energy. That's the little squiggly wave you see, which we call a gamma ray. And just like that, the nucleus settles down into a stable daughter nucleus.
Now this, right here, is the absolute key. Unlike other kinds of decay, gamma decay doesn't change what the element is. A carbon atom doesn't suddenly become a nitrogen atom. It is still the exact same element, same number of protons, same number of neutrons. It's just calmer. It's a de-excitation, not a total identity change or a transmutation.
Okay, so now that we've got the basic picture, let's get a little more formal. If an overexcited nucleus is the problem, then gamma decay, this release of pure energy, is nature's incredibly elegant solution.
To put it simply, gamma decay is pretty much the universe's way of settling an energy debt. The nucleus sheds its extra baggage by shooting out a super high-powered photon, which is just a particle of light, and we call that a gamma ray. You'll see it represented by that Greek letter, gamma.
This little comparison chart makes the difference crystal clear. Alpha and beta decays, they're kind of messy. They're ejecting actual physical particles, changing the whole identity of the element. Gamma decay, on the other hand, is so clean and precise. It's just energy. No change in protons, no change in neutrons, just a shift from a high-energy state to a low-energy one.
All right, let's take a quick look at the blueprint for this whole process. We're going to use a really simple equation to see exactly what's happening. And don't worry, it's very straightforward, and it gives us the perfect language to describe this incredibly elegant process.
And here it is. So on the left, you see X with that little asterisk next to it. That star is just a shorthand to show it's in that excited state. A is the mass number, Z is the atomic number. Now look what happens after the decay. A and Z are exactly the same. The only things that have changed are that the little star is gone, meaning the nucleus is relaxed, and a gamma ray has been sent flying. It's a beautifully simple equation for a pretty profound event.
Okay, now this might look a little complicated at first glance, but I want you to just think of it like a staircase. At the very top, you have an excited cobalt-60 nucleus. It can't just leap all the way to the ground floor in one go. Instead, it takes a couple of steps down. And with each step, it releases a gamma ray with a very specific amount of energy. You can even see the values there, 1.17 MeV and 1.33 MeV, until it finally gets to the stable state at the bottom.
And the energy of that gamma ray, it's not random at all. It is precisely the difference between its initial high energy level, EI, and its final lower energy level, EF. The nucleus lets go of the exact amount of energy it needs to get to that next stable step. This makes the whole thing incredibly predictable.
And this predictability is absolutely crucial for how we use it. For example, if we know a gamma ray has an energy of, say, 2 mega-electron volts, which is just a unit for a ton of energy at the atomic scale, we can calculate its exact wavelength. And it turns out to be ridiculously tiny, which is the signature of its high energy and its incredible power to punch right through materials. That predictability is what lets us harness it.
So this isn't just some fascinating physics concept, okay? This is technology that is actively changing our world. Let's dive into how we've actually learned to harness these powerful bursts of pure energy.
And the applications are just amazingly diverse. I mean, we are talking about saving lives in hospitals, peering deep inside jet engines to find tiny flaws, keeping our food safe to eat, and even pushing the absolute boundaries of scientific research. Gamma rays are an invisible but incredibly powerful tool.
This is one of the most important applications, hands down.
Remember that cobalt-60 from our little energy staircase? Its super predictable gamma-ray emissions are the cornerstone of radiotherapy. Doctors can use something called a gamma knife to focus these rays with pinpoint accuracy to just destroy cancer cells while leaving the healthy tissue around them unharmed. It is a revolutionary tool in the fight against cancer.
And then you've got this stuff, technetium-99m. It's a special version or isotope of an element that emits gamma rays. These rays can be picked up by a special gamma camera, letting doctors create images of our organs and actually see how they're working in real time. It's like giving doctors a superpower, X-ray vision for how your body is functioning, helping them find diseases without ever making a cut.
Of course, with great power comes the need for great caution. Because gamma rays are pure energy, no mass, no charge, they are unbelievably penetrating. They can slice through a lot of materials like they're not even there. And that's why we have to rely on really dense stuff, like lead or super thick concrete, to safely contain and direct them, making sure that power is only used for good.
So, to wrap this all up, let's do a quick-fire recap of the most important facts about this whole amazing process. I want you to think of the gamma ray as a kind of ghost particle. It's there, it has a massive impact, but it's totally unlike any matter we're used to. This table sums it all up perfectly. Take a look. Zero mass, zero charge. They travel at the ultimate speed limit in the universe, the speed of light. They're also incredibly good at penetrating things. And the decay itself happens almost instantly. We're talking trillionths of a second. It's a truly unique character in the particle world.
And here is a mind-bending little fact for you. Even though gamma rays have absolutely no mass, they have momentum. They can actually push things. I know, it sounds crazy. This comes straight from Einstein's theory of relativity, and it proves that pure energy itself can exert a force. It's just a beautiful, strange, wonderful little quirk of physics.
So, we end on this thought. We have a particle with no mass and no charge. It's made of pure energy, born from an excited atom. It travels at the speed of light, and we can use it to both see inside our bodies and to heal them. It's such a fundamental piece of our universe, and it just makes you wonder, what other secrets are out there, waiting to be unlocked? Thanks for joining me on this journey into the heart of the atom.